Welcome friends. In the previous session, we have studied simple graphs and pseudographs. We also discussed loops and multiple edges. Next, we are going to study degree of a vertex. Let us define degree of a vertex. Let G be a graph with a vertex set V and edge set E. Let V be the vertex of G. The number of edges incident with the vertex V is called degree of V and is denoted by deg of V or d of V. If degree of V is an even number, then V is said to be an even vertex, and if degree of V is an odd number, then the vertex V is an odd vertex. A vertex of degree 0 is said to be an isolated vertex. A vertex of degree 1 is called a pendant vertex. For calculating the degree of a vertex, each loop counted twice. An empty graph is a graph in which all vertices are isolated. For example, degree of A equal to 1, degree of B equal to 5, degree of C equal to 4 and degree of D equal to 3, degree of E equal to 3. Here C is the only even vertex. Vertices A, B, D and E are odd vertices. The vertex A is a pendant vertex. For the next graph G, here degree of V1 equal to 3, degree of V2 equal to 4, degree of V3 equal to 3, degree of V4 equal to 3 and degree of V5 equal to 1. Here V1, V3, V4 and V5 are odd vertices and V2 is an even vertex. Also the vertex V5 is a pendant vertex. Next problem, find the degree of each vertex of the following graph G. How many odd vertices and how many even vertices? Here degree of A equal to 4, degree of B equal to 2, degree of C equal to 2, degree of D equal to 5, degree of E equal to 3, degree of F equal to 0. Here A, B, C and F are even vertices and D and E are odd vertices. Subgraphs. Let H be a graph with the vertex set V of H and edge set E of H, and G be another graph with the vertex set V of G and edge set E of G. Then we say that H is a subgraph of G if V of H is a subset of V of G and E of H is a subset of E of G. In such a case, we also say that G is a supergraph of H. For example, Here G1 is a subgraph of G2 and G1 is a subgraph of G3, but G3 is not a subgraph of G2. From the definition we get every graph is a subgraph of itself. Then next is a proper subgraphs and a spanning subgraph. Let H be a subgraph of G if V of H not equal to V of G and E of H not equal to E of G, then H is called a proper subgraph of G. And if V of H equal to V of G, then H is called a spanning subgraph of G. That is, H and G have exactly the same vertex set. In the figure, G1 is a proper spanning subgraph of G3. If we delete vertex or edges from a graph G, we get different subgraph from G. Consider the graph H, G and K. H and K are the subgraph of G. Next, we discuss complete graphs. Definition: a complete graph is a simple graph in which each pair of distinct vertices is joined by an edge, provided there are no loops and no parallel edges. The complete graph on n vertices is denoted by Kn. Complete graphs for n equal to 1, 2, 3, 4, 5 and 6 given by K1, K2, K3, K4, K5, K6. Next, the complete graph on n vertices has n into n minus 1 divided by 2 edges. Since each vertex is adjacent to another n minus 1 vertices, so a total of n into n minus 1 edges, but divided by 2 since for the edges Vi Vj equal to Vj Vi. Any simple graph on n vertices is a subgraph of a complete graph K. For take K3, this is K3. Any simple graph on 3 vertices is a subgraph of K3. Next, we discussed bipartite graphs. Definition: let G be a graph. It is said to be bipartite graph if the vertex set V of G can be partitioned into two non-empty subsets X and Y. That is, X union Y equal to V and X intersection Y equal to empty, in such a way that each edge of G has one end in X and one end in Y. The partition V equal to X union Y is called a bipartition. Example: the complete graph K2 K2 is a bipartition with X and Y, and this is also a bipartition X1, X2, Y1, Y2. Next, consider the graph X1, X2, X3, X4, Y1, Y2, Y3, which is a bipartite graph. Here X equal to X1, X2, X3, X4 and Y equal to Y1, Y2, Y3. This graph redrawn as x1, x2, x3, x4, y1, y2, y3. x1 adjacent to y1 and y2, x2 adjacent to y1, y2 and y3, x3 adjacent to y2 and y3, x4 adjacent to y3. Consider the graph. x1, y1, y2, x2, x3, y3, y4, x4, which is a bipartite graph. Redraw. x1, x2, x3, x4, y1, y2, y3, y4. x1 adjacent to y1, y2 and y4, x2 adjacent to y1, y2 and y3, x3 adjacent to y2, y3 and y4, x4 adjacent to y1, y3, y4. From the definition of bipartite graph, we get it does not contain loops, but many contain multiple edges. Next, we discussed about complete bipartite graph. Definition: a complete bipartite graph is a simple bipartite graph G with bipartition V equal to x union y, in which every vertex in X is joined by every vertex of y. For example, here x1, x2, y1, y2, and x is adjacent to every vertex of y and x2 is adjacent to every vertex of y. If the vertex set X has m vertices and the set Y has n vertices, such a graph is denoted by Kmn. Kmn. That is, Kmn is a notation of complete bipartite graph with m vertices and n vertices. Since each of the m vertices in X is adjacent to each of the n vertices in Y, Kmn has mn edges. Now, we discuss complete bipartite graphs. Definition: a complete bipartite graph is a simple bipartite graph G with bipartition V equal to X union Y, in which every vertex in X is joined to every vertex of Y. If the vertex set X has m vertices and the set Y has n vertices, such a graph is denoted by Kmn. Since each of the m vertices in X is adjacent to each of the n vertices in Y, Kmn has mn edges. For example, x1, x2, y1, y2, x1 is adjacent to each of the y and x2 is adjacent to each of the y. This K2, 2. Examples of complete bipartite graph: K18, K33, K2 to K11. Clearly, complete graphs are not complete bipartite graphs, and in general complete bipartite graphs are not complete graphs also. The only complete bipartite graph which is complete is K2. Euler's theorem. The sum of the degree of the vertices of a pseudograph is an even number and equal to twice the number of edges. In symbols, if G equal to V E is a pseudograph, then sigma V belongs to V, d of V equal to 2m. Proof. Since each edge has two end vertices, when we calculate the sum of the degree of the vertices, each edge is counted twice. Note that even a loop contributes 2, although the two ends are identical. Hence, the sum is twice the number of edges. Corollary. In any graph G, there is an even number of odd vertices. In other words, the number of odd vertices in a pseudograph is even. Proof. Let x be the set of even vertices of G and let y be the set of all odd vertices of G. X be the even vertices and y be the odd vertices. Then V equal to x union y, where V is the vertex set of G. Then for each u belongs to x, d of u is an even number, and so the sum sigma u belongs to x, d of u is an even number, being the sum of even numbers. Also, sigma u belongs to x, d of u plus sigma w belongs to y, d of w equal to sigma v belongs to v, d of v, which is equal to 2m by the Euler's theorem, where m is the number of edges of the graph G. Thus, sigma w belongs to y, d of w equal to 2m minus sigma u belongs to x, d of u is even, being the difference of two even numbers. As all the terms in sigma w belongs to y, d of w are odd and the sum is even. So, there must be an even number of term in the sum. Hence, the number of odd vertices in a pseudograph is even. Next is verification of Euler's theorem. Consider the graph. Here d of V1 equal to 3, d of V2 equal to 4, d of V3 equal to 3, d of V4 equal to 3 and d of V5 equal to 1. So, sigma V belongs to V, d of V equal to 14, which is equal to 2m, where m equal to 7. Note that a loop is one edge, but it is added 2 to the degree. Next, define, let G be a pseudograph with n vertices. Suppose that d1, d2 etc. dn are the degrees of the vertices of graph G, ordered so that d1 greater than or equal to d2 greater than or equal to etc. greater than or equal to dn. Then d1, d2 etc. dn is called the degree sequence of G. For example, the degree sequence of K33 is 333 333. For this graph, the degree sequence is 4 3 3 3 1. Here degree of V1 equal to 3, degree of V2 equal to 4, degree of V3 equal to 3, degree of V4 equal to 3 and degree of V5 equal to 1. If for some positive integer k, degree of v equal to k for every vertex of v of the graph G, then G is called a k regular graph. A regular graph is a graph that is k regular for some positive integer k. Examples of a 0 graph, 1 regular graph and 2 regular graph. The complete graph Kn is n minus 1 regular, since each vertex is of degree n minus 1. The complete bipartite graph Knn is n regular. Some 3 regular graphs are here. Also, for any simple graph, the number of edges is always less than or equal to n into n minus 1 divided by 2, where n is the number of vertices. Now, we will do some problems related to this. First problem, prove that there does not exist graph with the degree sequence 3, 2, 2, 1, 1 and 7, 6, 3, 3, 2, 1, 1, 1. For the sequence 3, 2, 2, 1, 1, the degree sum is 9, not an even number. Hence, by Euler's theorem, such graph does not exist. For the sequence 7, 6, 3, 3, 2, 1, 1, 1, suppose there exists a graph with the degree sequence 7, 6, 3, 3, 2, 1, 1, 1. Let u and v be the vertex with the degree of u equal to 7 and degree of v equal to 6. Let try to draw such a graph. Here 8 vertices are here and 2 of our degree 7 and 6, but here the degree sum is 24. There is not a sufficient condition. Let us try to draw such a graph. Here u, v are here, a, b, c, d, e, f are 8 vertices. Then u have degree 7, 1, 2, 3, 4, 5, 6 and 7, and we have degree 6, 1, 2, 3, 4, 5, 6. Check the graph, the degrees are 7, 6, 2, 2, 2, 2, 2 and 1, but our question 3 of them are 1 degree, which is not possible. Next problem shows that in any group of n persons where n greater than or equal to 2, there are at least 2 with the same number of friends. Solution: denote the n persons by v1, v2, etc. vn. Let G be a simple graph with a vertex set v equal to v1, v2, etc. vn, in which 2 vertices vi, vj are adjacent if and only if the corresponding persons are friends. Then the number of friends of vi is just the degree of vi in G. Hence, to solve the problem, we must prove that there are 2 vertices in G with the same degree. Then the degree of the vertices of G must be all distinct. Let them be 0, 1, 2, etc. n minus 1 in some order. However, a vertex of degree n minus 1 must be adjacent to all the other vertices of G, and consequently, there cannot be a vertex of degree 0 in G. This contradiction shows that the degrees of the vertices of G cannot all be distinct, and hence at least 2 of them should have the same degree. Next problem. Prove that it is impossible to have a group of 9 people at a party such that each one knows exactly 5 of the other in a group. Solution: if we consider each member as a vertex, then the degree of each vertex is 5. Since there exist 9 people, the sum of the degrees is 9 into 5 equal to 45, which is not an even number. So, by Euler's theorem, it is not possible to have a group of 9 people at a party such that each one knows exactly 5 of the other in the group. Next problem is, let G be a graph with n vertices, T of which have degree k and the other have degree k plus 1. Prove that T equal to k plus 1 into n minus 2m, where m is the number of edges in G. Solution: V1, V2 etc. Vn be the vertices of the graph G. Then sigma I equal to 1 to t, degree of Vi equal to Tk, and sigma I equal to t plus 1 to n, degree of Vi equal to n minus t into k plus 1. But by Euler's theorem, sigma I equal to 1 to n d of Vi equal to 2m, that is Tk plus n minus t into k plus 1 equal to 2m, implies t equal to n into k plus 1 minus 2m. Next problem is, let G be a graph with n vertices and exactly n minus 1 edges. Prove that G has either a vertex of degree 1 or an isolated vertex. Solution: let V1, V2 etc. Vn be the n vertices of G. Then sigma I equal to 1 to n, d of Vi equal to 2 into n minus 1. I equal to 1 to n, d of Vi equal to 2 into n minus 1. Suppose degree of Vi greater than or equal to 2 for all Vi belongs to V of G. Then sigma I equal to 1 to n, d of Vi is greater than or equal to 2 into n, implies 2 into n minus 1 is greater than or equal to 2n, which is a contradiction. Hence, G has either a vertex of degree 1 or an isolated vertex. Next problem, what is the smallest integer n such that the complete graph Kn has at least 500 edges? Kn has n into n minus 1 divided by 2 edges. Given n into n minus 1 divided by 2 greater than 500, implies n into n minus 1 greater than 1000, which is implies n square minus n minus 1000 greater than 0. Solve for n, we get n greater than 32.15. Hence, n equal to 33. Now, let us summarize this session. In the class, we have discussed Euler's theorem and its applications. In the next class, we will discuss graph isomorphism. Thank you for watching this session. See you next time. Until then, bye.